All right, here we go. In 1980, what was the biggest thing that happened? Well, you kind of know, because you know the title of the talk. It was Rubik coming out with his cube, the famous Rubik's Cube. From one day to the next, basically, the world turned into one big, huge Rubik's Cube. And pretty much everybody, and I say everybody, was playing with their cube for a couple of weeks, and basically everything came to a standstill. There was only cubes to be seen and cubes to be handled all over the world. No different from me. I was growing up at the time. I was still going to school. My parents gave me a Rubik's Cube, and I spent 3 weeks pretty much non-stop trying to solve it. So after 3 weeks, I was actually able to do the Rubik's Cube. So give me any Rubik's Cube, scramble up, and I was able to solve it. So, I mean, this sounds pretty much like the end of the story. For most people, I mean, there was a lot of people who kind of managed to solve the Rubik's Cube at some point in time. And, well, anybody here who can solve the Rubik's Cube? Okay, so pretty much end of the story. Well, not really, not really. I mean, at least not for mathematicians, and also for the world at large. This thing kind of appeared just like a kind of a Mount Everest rising all of a sudden, and it had to be conquered. Well, we conquered it, but what do we actually mean by this? What do we mean by solving? Solving. Well, I solved it by not looking at anybody else's solution. I actually, figured out a solution myself. I mean, you can all solve this quadratic equation here because somebody in school told you you need to use the quadratic formula and it gives you the answer. But who actually figures out those quadratic formulas in the first place? Well, that's mathematicians, right? That's mathematicians like myself. And like the Rubik's Cube was really kind of, if I think back, it was really the first really, really, really big problem that I kind of solved by myself. It was a very mathematical toy. It was a very mathematical challenge, and it took me 3 weeks nonstop to figure it out. And in some ways, that made me a mathematician because I was really working as a mathematician at the time. And it actually happened to a lot of my colleagues too. So the Rubik's Cube had a huge influence on the development of a lot of mathematicians as they were growing up. But also as a kind of an icon, it was something that was a challenge. It was a challenge to conquer. Well, I mean, the first people who actually figured out solutions were basically mathematicians. I talked to some of my older colleagues. They took time off from their work to fly to Hungary to buy some of these things, brought them back and made a lot of money by selling them to their other colleagues. So there was lots of things there that needed to be figured out until recently, actually. And I'm still, even today, there's lots of things that need to be figured out. And I want to talk a little bit about those things. Okay, so first of all, what's the big deal? What's the big deal? Well, let's just take one of those cubes and take it apart. Okay, let's have a really, really close look at it. And at this point in time, I'm actually going to take a Rubik's Cube and, basically take it apart, and you can have a camera kind of just pointing at it, and, you can see me kind of taking it apart piece by piece. Okay, so what we've got here is basically 8 pieces correspond to the corners of the cube, corner pieces, and then there are the edge pieces, 12 of them. And then in the middle, there is this cross. You can see it, this 3D cross. And that 3D cross actually doesn't change at all while you're solving the cube or while you're scrambling the cube. Okay, now let's just see. We have got all these pieces now. We've got the cross in the middle. And so what we want to do now is basically just put on a blindfold and ask somebody to slot those things back in again, just randomly, so that eventually you've got something cubical in your hand. So in how many different ways can you actually do this? Well, there's a few. It's this many, right? It's huge. It's huge. So it's that many different ways in which you can put the cube together. Now it actually turns out that not all of those positions can actually be solved with legal moves by just twisting the cube. So when you kind of put the cube randomly together, you've only got a 1 in 12 chance of doing this. Oh, wait. So let's just do this again. So we've got this big, huge number here. And how big is it actually? Well, this number is huge. It's basically the number you get when you measure the surface area of the Earth in millimeter squares. Or in other words, if you take like that many Rubik's cubes and put like all the different combinations, all the different positions into those Rubik's cubes, and then scale them down to just this tiny 1 millimeter times 1 millimeter times 1 millimeter, then you can take all those Rubik's cubes, all those configurations to cover the surface of the Earth. That's pretty, impressive, I would say. Okay, so in many ways, when you're kind of dealing with the cube, you're dealing with this sort of complexity. When you solve it, right, you have to be able to solve all of those things, and all the other questions that you might want to ask, you have to be able to deal with this number. Now, this number is actually maybe a bit too big because there's only, not all of these combinations or all of these positions can actually be solved with legal moves by twisting the cube. The number that can be solved is this. Well, still pretty amazing. And actually those two numbers are related. You just divide the first number by 12 and that gives you the second number. And so what that actually also says is that if you randomly assemble a cube, you've got a 1 in 12 chance of actually being able to solve it if you know how to solve the Rubik's Cube with legal moves. Okay, good. Now, what I want to do first is kind of mathematically, I'll just tell you a little bit about how we mathematically make sense of these numbers here. So how do they come about, okay? And that introduces you to a lot of different concepts in mathematics. And that will get us closer to like the main question about the Rubik's Cube, which has puzzled mathematicians for a long, long time. All right, here we go. So how do we get this number? Well, let's have a look at those 8 corner pieces, okay? Those 8 corner pieces, they take the first one that can go into 8 different positions in the cross, so 8 different corner positions. Now, once we've decided where we want to put that one, we take the second corner and slot it in. Well, since one corner position is already occupied, we've already got 7 positions left over, so that's so far 8 times 7 different ways of slotting in the first 2 corners. Then there's 6 positions left over for the third corner, so that makes 8 times 7 times 6 different ways of slotting those 3, and then it keeps on going like this, so 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 different ways of putting those corners back into the cross. Okay, and this has a special name, this number is called 8 factorial. So that's just 8 times 7 times and so on, right? Okay, but then every of those corners has 3 colored squares, and so we can orient a corner in 3 different ways. So the first one can be oriented in 3 ways, the second one in 3 ways. That makes a total of 3 times 3, 9 different ways, and then the third one another 3, so it's 3 times 3 times 3. So a total of 3 to the power of 8 different ways of orienting those corners. And so what we've got so far is just kind of putting the corners in. You've got that many possibilities, 3 to the power of 8 times 8 factorial. Okay, same sort of numbers come out when you slot in the edge pieces. So edges are 12, so we get 12 factorial, so that gives another factor of 12 factorial. And then every edge can be oriented in 2 different ways. You can flip it in 2 different ways. So that gives 2 times 2 times 2, so 2 to the power of 12 different possibilities. And that's the number on top. That's the number, that huge, humongous number that starts with 519. Okay, now where does the 12 come from? Where does the 12 come from? Actually, you can account for the 12 very nicely. So 12 is 2 times 2 times 3, and I can actually tell you exactly where those factors go missing. So let's just first have a look at the 3. Okay, that has to do with corners again. It has to do with the way you slot in, you kind of orient the corners. So before we said, well, you put your corners in and then you kind of orient them like one at a time, the way you want them, right? What does that Well, what does that mean here? I mean, what I'm indicating here basically means that, well, yes, you can basically do whatever you like with the first 7 of your corners, but once you've put those in some position, in some orientation, the last one, the orientation of the last one is actually completely pinned down. You don't have a choice. If you put them in one way, it's going to be okay in the end, but if you put them in any other way, you can be sure that your cube can't be solved. And I just want to give you a bit of a hint of how this works. Okay, so at this point in time, I'll show this cube here, and I explain. So what I'll do is, there's something happening in the cube, kind of a special sort of dance that happens in the cube whenever you manipulate it. So if we start with a solved cube and we label it, right? So we take like the yellow side and we put zeros here in these positions, and then we go opposite and also put zeros there, and then we go around every corner and write 0, 1, 2 in the clockwise direction, and then we basically get this cube here. So if we just focus on this thing here, now I'm going to scramble it up a little bit. So scramble it up, and to start with, we find that, well, if we add up the numbers on the top and at the bottom, what do we get? There's only zeros there, so we get a 0. If we go for all the numbers on the left and the right, what do we get? Well, we can see here 1 plus 1 is 6, plus 2 plus 2, that's 1 plus 2, 1 plus 1 is 2, plus 2 plus 2 is 6. And on the other side, you actually get the same pattern happening, so it's a total of 12. And front and back is the same sort of thing. So if you take two opposite faces, you once get 0 as a sum, and otherwise 12. Now, if we scramble it up, we can again scramble it up, kind of toss it up in the air. You choose any two opposite faces of the cube now, and add up the numbers. Okay, and you just do this, and the first person gets, well, maybe they get 6. The second person gets 9. The third person gets 15. Whatever. But all these numbers have something in common. So we've seen like 0. We've seen 6. We've seen, it's all what? It's all multiples of 9. Okay, so it's all multiples of 9. It's all multiples of 3. So it's all multiples of 3. And, well, that happens in the background while you're manipulating a cube. Okay? So you can think of a cube as having those invisible labels on them, right? So those invisible labels, 0, 1, 2, 3, around all the cube faces. And when you scramble it, even though you don't see them, but the labels will always add up to a multiple of 3 when you look at opposite faces. Okay, what does that mean? What does that mean for orienting the corner pieces? Well, that means let's just put in 7 of them, okay? And then choose 2 sides and add up whatever's there at the moment. And maybe that adds up to 8, right? That's up to 8. And now we have to put in the last corner, and you have to make sure that things stay legal. And so what do we have to make sure that it's on top? 0, 1, or 2? Well, the number has to, when you add that number to 8, you have to have something that's divisible by 9. So the only choice we really have is to go for the 1, right? So we have to put that last piece in this one particular way to ensure that we've got a sum that's divisible by 3. Okay, so that forces one of those 3's out. Something very similar happens with the edge pieces. So you can basically put edge pieces in, and then the orientation of the last one. So you put like oriented 11 of your edge pieces, and the last one is determined by the choices you make for the first 11. Okay, so it's pretty much exactly the same thing. And then there's one more 2 that falls out, and that has to do with a different sort of a dance that goes in the background, and that's something very, very important. That's something like an incarnation of yin and yang in mathematics. It has to do with the way scrambled up things can be sorted out by swapping swapping things. So, for example, I mean, you've got like here a couple of people in a row. They're scrambled up. You want to put them in order so that the tallest one comes first and the second tallest one and so on. So usually what you would do is you just kind of swap two people around, then you swap another two people around, you swap another two people around until they're in this order, until the people are in this order. And now it actually turns out that whenever you do something like this, there's lots of different ways of arranging something in order like this, but all of these different ways for one particular mess up have one thing in common. They either all take an even number of swaps or all take an odd number of swaps. So it's kind of an odd and even for messes, and that comes into play when you consider the Rubik's Cube too. So there's another odd and even factor of 2 that goes missing here. So basically, once you fit it all in all the corner pieces, you put them in any way you want. The orientation is then fixed somehow. When you put in the edge pieces, you actually have to be a little bit careful that you don't have two things swapped where they shouldn't be swapped. Anyway, so that takes care of all of it, and takes care of it in a very mathematical way. And you've got something here at work. These invariants, they like whole branches of mathematics are basically about these invariants that tell you vital information about mathematical structures. Okay, now so we've got this all under control. We know where the huge numbers come from. Now we have a look at all of these combinations that we can create now, all the valid ones, right? And we ask, can we actually say how many moves it takes in the worst case scenario to solve all of them? Okay, so you can just think again. You've got like all of those configurations maybe lined up right next to each other, and on every single one of the cubes that has one of those configurations, we just write the number of minimal moves that it takes to sort out one of those configurations. And you look at all these numbers. So what's the largest one? That's the worst case scenario. And how many of those large ones are there? And how likely is it that you hit one of those worst case scenarios? Or if you've got one of those scenarios and just pick up a random one, what's the number you can expect? What's the average or something like this, right? So this is all very kind of natural questions, and in some ways this is something that mathematicians will want to know, especially all those mathematicians who grew up with the Rubik's Cube. But also it's one of those things that kind of society as a whole wants us to answer. It's one of those questions that kind of comes up naturally, and it's really like climbing up on Mount Everest, right? So can you really do this? Can you really do this? So you mathematicians, you think you're so smart. Can you really, climb up that mountain? Can you get these huge numbers of configurations under control? And well, it took about 40 years, but it's just been done recently. People now know the answer to all those questions. And here the table basically tells you what the answer is. The worst case scenario is 20. And well, there's actually a couple of million of those, about 500 million of those worst case scenario configuration. That's quite a few. Now, if you have a look at it, actually all bunches up very closely to this 20. So I mean, the most likely number they can get here is about 18. You can see that there. And it kind of dies out very rapidly down towards 0. Now, how could you actually figure this out, right? I mean, it's got this huge number of configurations. So what you think people should do is just look at every single one of the configurations, figure out minimal number of moves, and then compare all those numbers and get worst case scenario out and do the statistics here. But actually, that's just completely impossible. It's completely impossible. It would take until the end of all times to actually go through all the possibilities, even with computers that maybe like in 100 years, we have in 100 years, we won't be able to kind of go through all those possibilities, although you have to be a bit careful when you say these sorts of things. So there's no way you can do this, um, at least not with what we've got at the moment. So you've got to be very smart about it, or you've got to have a very good idea. And actually, what we're facing here, or what we've been facing here as mathematicians, has been very similar to a kind of a different but very prominent, also very iconic problem in the history of mathematics. And that was in World War II. In World War II, the Germans used the famous Enigma cipher machine to encrypt their messages. And the Enigma cipher machine has about as many positions to be set up as the Rubik's Cube has configurations. And basically, to crack the ciphers, you had to every day figure out which one of those positions the German actually set their machines to. And so how was this actually done? Well, the way it was done was a combination of kind of brute force computing. So they actually built the first computers to deal with a lot of stuff. And so what they went through there on every day was like a million different possibilities. But of course, a million is very far away from this huge numbers that we're dealing with. So what actually happened, what they were actually able to do by some really, really smart thinking, by some very mathematical kind of thinking, was to subdivide the problem into a million parcels. And every one of those parcels, of course, contains zillions of different configurations. And so what you were able to do was to kind of mechanically kind of say, well, we're looking at this first parcel here, and then very quickly decide, without looking at every single piece in here, whether your setup configuration was in here or not. Basically, in a second, in a microsecond, you could decide this. Then you move on to the next one, move on to the next one. So you really had some very smart insight into the structure of the Enigma machine happening here, and that was translated into being able to break down the problem into basically a million steps. And so something similar happened with the Rubik's Cube. So again, you have this huge number of configurations, but if you're just really, really smart, you can actually parcel them up again and kind of calculate through them very, very quickly by just kind of looking at, one or two representatives in each of those parcels. That's actually exactly what happened, right? And so people now know, after doing a lot of computation, but also being very, very smart, what the answer to this question is. Okay, now I could stop here, but let's see whether we can do something else. So we'll go to the next slide here. Just go to the next slide. Now, I can't really tell you what these smarts inside are that went into solving the Rubik's Cube, but I can tell you about a smart insight that actually makes solving the Rubik's Cube very easy. Well, not easy, but doable, okay? And it's a similar sort of thing, right? I mean, most people, if they're halfway persistent, what they get to in the Rubik's Cube is they get to solving like one of the layers, okay? So they can do one layer, and that one layer then is it, right? So they don't get any further, because if you go beyond anything there, what happens is you get stuck, right? You get stuck, you immediately destroy what you've done before. So what you really need, you need to be able to design algorithms that can leave whatever you've created so far, whatever you've put in order so far, leave this in peace and manipulate only small parts of the cube, okay? And so how do you design these things? Well, there's one really fundamental insight. It's one of those things where you can be really, really smart. It's a very mathematical thing. It's called a commutator. And I just want to demonstrate to you how this works. And then you can actually go home and, well, you still need to put in some effort. The effort is going to be to figure out for yourself how to do the first layer, okay? And then comes the smart bit comes in. The smart bit comes in. So you can apply the smart bit to actually try figure out your own algorithms to do the whole cube, to take care of everything. All right, so here is how this goes. So I'll show the cube at this point in time, and I'll say, if you are at the stage where you can solve the first layer, then you are kind of the master of the first layer. Your master of the first layer means you can do anything you want with the pieces on the first layer, as long as you don't worry about what else goes on in the cube. So you take your cube and you rip out one of the corners, for example, or rip out one of the and kind of turn it over. You can actually do this with legal moves as long as you don't worry about the rest. So maybe you're unsure about whether you can really do, but take my word for it. If you can do the first layer, you can do all those things. You can basically permute up this top any way you want, any orientation, any piece, wherever you want it, okay? So let's just say I give you the task to figure out for yourself. So we want the top to stay pretty much as it is. The only thing you want to happen is we want to take out one of those edges and we want to flip the orientation, okay? And you can do this. And if you're very systematic, you can actually note down exactly how this works, okay? So now unleash this move or this combination of moves on your cube, and yep, you did the right thing, very good. Now if you wanted to restore the cube, what would you do? What would you do? Well, pretty obvious. You just run the whole thing in reverse. That will restore the cube. Perfect. Okay, and here's this insight, this mathematical insight, the commutator insight. It's like this. So if we run it backwards, it will restore the cube. Okay. Now what we're going to do is, before we run things backwards, we give the top layer a quarter turn twist, and now we run it backwards. Okay. And the effect this has is exactly the same as before. The same, whatever piece was swapped, well, there's a different one in that position now, but that's the only thing that happens on the top layer. That gets swapped, and the bottom part of the cube gets restored. Okay, and so basically, once you've finished with your move, you can just do a reverse twist of the top, and that will have resulted in an overall effect of flipping two of the edges. And that's exactly one of those things that comes in very handy when you eventually arrange the orientations of the edges. You can do something similar for rotating corners. You can do something similar for just moving a small number of corners or a small number of edges. And you actually only need like four magic moves like this to solve the whole cube. And hopefully that gives you a bit of an insight into how mathematicians attack problems like this, and how we're successful in thinking our way through very, very complicated problems.